Hello everyone, today I will be talking to y'all about a photodetector called the Single-photon Avalanche Diode, also known as the Geiger mode avalanche photodiode. The Single-photon Avalanche Diode is essentially a PN junction that operates at a bias voltage above the breakdown voltage, where a photon-generated carrier can trigger an avalanche current because it has enough kinetic energy to promote an electron from the valence band to the conduction band, creating an electron-hole pair. This mechanism is known as impact ionization. Electron-hole pair generation is then sustained through positive feedback to cause the avalanche. Some of the motivations of using single-photon avalanche diodes are to increase the efficiency of photon detection and the spectral range at which a photodetector can detect. It is sensitive enough to detect a single photon. It also has relatively low power consumption. These points will be extended upon as I explain how the diode functions and how it stacks up when compared to other technologies used for photodetection. Now that we understand what a single-photon avalanche diode is, let's discuss how it works. So a photon is detected when it gets absorbed in the active area and generates an electron-hole pair. That pair must trigger an avalanche and the resulting current will be seen. As we increase the excess bias voltage, the efficiency of detecting photons also increases. This is because as voltage increases, it creates a higher electric field, so the probability that an electron-hole pair can cause an avalanche increases. A problem in detection is noise caused by the dark counts. A breakdown can be triggered by an incoming photon or by any generated free carriers, but we mainly want to focus on generation by incoming photons. Dark current rises when excess bias voltage increases because the greater electric field now also induces more generation of carriers within. To reduce thermally generated dark counts and ensure fast single-photon timing, single-photon avalanche devices tend to have small active areas to reduce the number of generations and recombinations. So at the applied bias, the electric field is so high that a single charged carrier injected into the depletion region has the ability to trigger a self-sustaining avalanche. The avalanche is diverging because the growth in the population of electrons and holes due to impact ionization is greater than the rate at which they can be extracted, leading to exponential growth of the current. This allows the avalanche current to rise so fast it's almost instantaneous, and the current is also so large that it can be detected, usually within the milliamps range. When the photon is detected, the leading edge of the avalanche pulse current signal marks the arrival time of the photon. We can see the detection times of many photon detections in the plot on the left as the edges leading to the peaks. The current continues to flow until the diode is quenched. Quenching is when the bias voltage applied is reduced back to the breakdown voltage, if not lower. Then there is a period between detections called the dead time where the device can recharge, and that period is usually a duration of at least 6 nanoseconds in today's technology. The dead time is also variable depending on if the diode is being quenched actively or passively. On the plot, that period would be right before the next leading edge. After quenching, the single-photon avalanche diode is reset by applying the bias again and ready to detect for the next photon. Here we can see where the applied bias is with respect to the breakdown voltage of the device. The difference between the breakdown and the applied voltage is the excess voltage. We can see the increase in current when the avalanche is triggered, the decrease in current and voltage when the device is quenched, and the reinstatement of the applied bias to reset the single-photon avalanche diode. So now that we've talked about how quenching affects the device, let's talk about the different kinds of quenching. First, there is passive quenching. Passive quenching has a simpler circuit. It has a lower counting rate of photons than active quenching, but it is sufficient for returning a detectable output. However, it is inconsistent at counting photons, so we often see varying magnitude of peaks in our output, as well as variations in the duration of the dead time between detections. Active quenching is a more complex circuit, but it improves the consistency of the duration of the dead time and the uniformity of the photons counted. There are also two types of single-photon avalanche devices, thin junction and thick junction. Both types have been improved with modern science to have low dark count rates, which decreases the noise in the output signal. For the thin junction diode, the breakdown voltage is much lower than for the thick junction. The thin junction's breakdown is in the range from 10 to 50 volts, while the thick junction's is from 200 to 500 volts. From the amount of voltage needed, we can see that the thick junction will have a higher power dissipation than the thin junction, and therefore requires a cooling process in order to keep the diode functional. The thin junction has a small active area up to 30 micrometers, while the thick junction has a wide active area of typically around 200 micrometers. Both have good photon detection efficiency in the visible range, but the thick junction has poor detection when the wavelength is near infrared, while the thin junction is still able to pick up the longer wavelengths. The timing resolution is significantly higher for the thin junction, coming in at around 100 picoseconds at full width at half maximum compared to 350. In terms of manufacturing, the thin junction only requires a standard grade silicon substrate, while the thick one requires ultra-pure, high-resistivity silicon, making it much more expensive to manufacture than the thin junction single-photon avalanche diode. Here you can see the two types and their varying dimensions and the differences in thicknesses of the device. As with any device, there are challenges and trade-offs with the functionality of the single-photon avalanche diode. In terms of physical processes that come with the diode, it is difficult to reduce timing jitter without sacrificing the size of the active area. This goes hand in hand with trying to increase photon detection efficiency. Instinctively, it is easy to assume that increasing the depletion region of the diode will allow us to increase the photon detection efficiency. But increasing the depletion region will also cause more timing jitter and noise. Another challenge is to reduce band-to-band tunneling in the single-photon avalanche diode. Doing so will improve dark count rates, photon detection efficiency, and timing jitter. In order to fabricate the device, contamination must be minimal. On average, current technology can limit defect concentrations to less than 10 to the 9th defects per centimeter cube. Impurities and crystal defects can cause after-pulsing and set off a positive feedback loop that significantly increases the dark count rate and noise. After-pulsing occurs when carriers are trapped and cause delay in the avalanche. Another limitation is that the electric field intensity is constrained by the level needed to set off the avalanche multiplication to reduce additional noise. The breakdown voltage is strongly dependent on the temperature of the junction. Under constant bias, excess voltage will begin to decrease with rising temperature, leading to the degradation of the device's performance. With a good sense of what a single-photon avalanche diode is, let's compare it to its competition. Photomultiplier tubes came before single-photon avalanche diodes. They are operated in high vacuum tubes with high voltages between its anodes and photocathodes, and an electron is produced from the photocathode from the photoelectric effect. One of the main motivations for using single-photon avalanche diodes when compared to photomultiplier tubes is because they have a wider spectral range of operation, especially nearing the infrared. Single-photon avalanche diodes also have better timing resolution. In terms of design, the single-photon avalanche diode does not need cooling when dealing with the infrared spectrum, while the photomultiplier tube will overheat unless cooled. The dimensions of the diode is also much less bulky, making an assembly of large arrays for detectors more feasible. Photomultiplier tubes are also more sensitive to electromagnetic disturbances and mechanical vibrations, and so making the device more stable requires more internal mechanical structures and therefore raises the price. When compared to the avalanche photodiode, the most obvious difference is that the avalanche photodiode needs multiple photons for a detectable light pulse. The single-photon avalanche diode operates above the breakdown voltage in Geiger mode, rather than below in the linear mode. Although they both use the avalanche effect, the single-photon avalanche is divergent, while the avalanche photodiode generates current proportional to the light received. The single-photon avalanche diode has a higher detection efficiency due to its smaller active area, and the smaller active area results in lower dark counts. The reset mechanism also differs between the two. Rather than quenching, the avalanche photodiode resets when the light source is extinguished and does not turn back on until the light source is turned on again. Here we can see the difference in generation between avalanche photodiodes and single-photon avalanche diodes. In the avalanche photodiode, the bias is below the breakdown voltage. It has a lesser electric field than that of the single-photon avalanche diode, but enough for a photon to generate an electron-hole pair that can then generate another. Below on the left, we can see an avalanche multiplication illustration in a space-time diagram. The electron on the left starts a chain of impact ionization events, and you can see the solid arrows for the electron trajectories and the dotted arrows for hole trajectories. On the right, we see operation in Geiger mode, where the growth in the population of electrons and holes due to impact ionization outpaces the rate at which they can be extracted, so we see an exponential growth of current. Now, to put everything into perspective, the photomultiplier tube was one of the first main commercial developments in photon detection. By 1936, they were high-performing and produced industrially. During the 1960s, the avalanche phenomenon in p-n junctions was discovered at the Shockley Laboratory, where they observed macroscopic voltage pulses triggered when a single photon was absorbed. By the 1970s, Robert McIntyre and Paul Webb had made significant developments on silicon avalanche photodiodes, where they observed generation of single photon pulses in their photodiodes when biased above the breakdown voltage. By 1975, single photon avalanche diodes were able to be actively quenched. Further developments were made in 1987 at the Rockwell International Science Center, when they developed the solid-state photomultiplier. This is an avalanche photodiode with very high donor concentrations that we now know as the visible light photon counter. In the 1990s, the metal resistor semiconductor was invented in Russia. In recent years, we see developments in single-photon avalanche diode arrays and germanium single-photon avalanche diodes to increase the spectrum of detectable wavelengths into the infrared. And here are some applications of single-photon avalanche diodes. They range from LiDAR to medical imaging and basically include any application where light needs to be focused on a precise region. So to wrap things up, let's revisit the motivations behind why we use single-photon avalanche diodes. They are relatively simple and small and power efficient compared to other photodetectors. They have the sensitivity of sensing a single photon and are very efficient in photon detection. And with advancing technology, continue to widen the spectral range at which it can detect photons. And here you can see some of the references that I used for this presentation. Thank you all for watching.